Good evening, everyone. So Peter asked for who it was the first time they are at this meetup, and that's me. I mean, so good. So about half of you don't have any quality indicator, and that's great because Peter also said that he has two great speakers, which means that there's apparently 2 more people after me, and I thought there was only 1. So this is going to be interesting. Let's see, let's get rid of some of this junk. I'm Frank, and I work at Google. In fact, I work right downstairs here on the 3rd floor in that corner. In case you get lost, I can walk you out after the event. I work on Firebase. I would normally be wearing a Firebase shirt, but people swore that I should wear this one. I expect lots of tweets of the shirt, by the way. And I don't normally do a lot of talks about Firebase and live coding stuff with that, but decided to spice it up a bit differently for you lot tonight. Oh, by the way, I'm Dutch, which you can hear from my accent, and I live in America, which you can see from the fact that I start my talk while chewing gum. Oh. Let's get rid of that. Yeah.
Stay out of the light.
Stay out of the light. I had warned them that I move around a lot, so this is going to be fun. Hey, we're going to be, wow, okay, this is the title that I ended up with. I said it was going to be something with geoqueries. That's pretty much what this should cover, so let's make sure we do that. Who knows what geoqueries are? Good. If I run into trouble, I'm going to actually ask you for help, just so you know. I'm not an expert, but I'm like a educated layman, I would say. Who has used Firebase before? Cool, I like that. I really like that. Just because there's so many, I didn't expect that. How many actually used Firebase before we were part of Google? Yeah, cool. Let's actually not spend too much time, otherwise I'm going to eat into Abe's time, which is never good. Let's see. Location-based apps. I think we talked a bit about that in the abstract for this talk, in the description. Who uses Lyft or Uber? Wow, there's hands not going up. Is there like other ride-hailing services that I don't know? I mean, could be, okay. One of the things I like about Uber Ride is that if I open the app, it shows me the cars that are around me. And then, right, I tell it to book me an app, and it turns out that they're not around me, they're further away. And then I see that the car is heading in the wrong direction, and I can cancel the ride. Right? This is sort of fun that you can in real time see where your driver is. So I really love that about it. The one on the right is a Pokemon Go app. Now, I'm pretty sure this is a screenshot from a while ago, because for one, there's not that many Pokemons, and I'm pretty sure we just had an update. But also because it shows Britney Spears at the bottom. I'm not sure if she's still performing in Vegas, actually. Okay, so what both of these have in common is that they show information from a database on a map, right? And they probably are only loading the information that actually fits in the viewport, which is an interesting type of database query on any database, but especially on NoSQL databases like the ones from Firebase. Who knows what this is, actually? It's going to be a bit hard to see, but... So these are all the e-bikes or e-scooters. So this is probably also old because I'm pretty sure they've been banned for a few weeks now. But ignoring that, this is all the e-bikes and scooters in San Francisco. I live in Sunset. No scooters around my neighborhood, unfortunately. But and this also, right, is just a big database of points of interest, and you query them for location. I was like, wait, I know this from Firebase because we had a demo for a long time that showed you in real time where public transport was in major cities. So this is in San Francisco, and apparently when I took this video, there were lots of line 14s on Market Street. There's also some weird rounding errors because they're not really on Market Street. I'm not sure how that works. But you can see that these are moving along. And this was a demo that runs on the Firebase real-time database. And we query all the objects in this circle, and we get real-time updates, which is one of the things, if you've ever used our database, that's what we're known for. We shut this demo down a while ago because essentially there's app builders that are way better at this than we are. But I'm quite sure quite a few of them still run on our technology. I was like, this is interesting. I want to learn more about how this works, especially with our newest database, like Cloud Firestore. So I was just like hacking on it. I was like, I need a use case. Right? So I was like, I want to, right? I imagine I have a map with lots of points of interest on it, lots of items. And I want to get the items that are within a range of 25 kilometers of Sacramento. And Sacramento, it's because it's the state capital, and I happen to know the location of that. That helped me a bit. And 25 kilometers, because not because I'm Dutch, but actually because most of the world works in kilometers. So, okay. So I want to get everything in this green circle, and believe it or not, but that's what we're going to be spending the next 30 minutes working on. So. Right, I didn't really tell you what we were going to do. So this is the program for tonight. Please don't take too many notes. We're going to go through them one by one. In fact, we've already covered number one, right? Location-based apps. We know what those are. So apparently, we're not going to look at storing locations in the database. Who has used the Firebase real-time database? Huh. Okay, who has used Cloud Firestore? Okay, we're going to be talking about Cloud Firestore. So Firebase has two databases, two NoSQL databases. Our classic one that we started with 6 years ago, I think, is the real-time database. Its unique feature is that it does real-time synchronization between clients. And we sort of liked that, but then we joined Google, and Google said we really liked that, but we wanted to scale even better. So that's what Firestore became. So Firestore is like if a cloud data store and Firebase real-time database got married and had a kid, that's Firestore. And this is a screenshot of Firestore in the Firebase console. And to do this type of querying of data on a map, right, from a database and put it on a map, I need a database and I need some sample data. So let's quickly have a look at what we have. Okay, wow, we have tiny text. If at any point my slides or my text is not readable, just like raise a hand or yell at me, because I sometimes forget, but I'll try to remember. Is this readable for the folks in the back? No, ouch. Let's see. It's the best I can do. It stopped zooming in, so thank you. Okay, so this is the Firebase console. The Firebase console is where you manage your Firebase projects, and I have quite a few Firebase projects. And this one is called Large Firestore. So I guess it's the project where I store a lot of data in Cloud Firestore. That's a pretty certain thing. So you see all kinds of Firebase products on the left. So we have authentication, database storage, all kinds of backend services to build products. We also have crash reporting products like Crashlytics, and we have performance monitoring, and we have analytics products and products that help you grow your app. We're not going to look at those. Don't worry. This is not a Firebase overview. We're going to focus on only one or two of these. So one of the databases we have is Cloud Firestore. We also have the real-time database, but I'm not using that for the demo right now. Okay, so this is the actual data in my database. So Cloud Firestore is a document database. So it stores documents in collections, and then you can nest collections under the document again, and then you can build a nice tree of all kinds of data. So on the left, you see my top-level collection. So I have something called 10K, 1K, and this number. I'm quite sure we'll have a raffle prize for anyone who realizes what type of number this is. And then this is the list of documents I have, and these are the documents that I generated. So I generated 10,000 documents and gave them all kinds of random properties. Really, it doesn't really matter all that much what I did. So I gave them a color so that I could filter on color. I gave them a counter, which is literally, I think, how often I clicked on it, but it sounds unlikely that I took 6,000 clicks. Then again, I'm a cookie clicker addict, so who knows? It has an index and a location, and the location is the one that I want to look at. So what I did is I have a list of all the state capitals and their locations, and actually of all the states with their capitals and their locations, and I entered that into Firestore. Right? How do you store location information in the database? If you use the real-time database, you store them as two float numbers. That's literally it. There is no specific type. Cloud Firestore has a geopoint type, which not surprisingly stores a latitude and a longitude. Now, I've been having the hardest time to remember which one is up and down and which one is left and right. Who knows? Latitude is up and down, as far as I know, yeah. So I think I got that right. If I make a mistake, don't call me out on it. It's sort of embarrassing. So I gave all of these a random location around the state capital that I placed the document in. So I took the point of the state capital and then went a bit up and down, left and right, some sort of box around the state capital. This becomes important later. So I have a map with 10,000 documents in the United States somewhere. So let's go back to the slides. So let's see. I think that covers storing locations in the database. I mean, not all of them are this simple, but this is pretty much the easy one. Which means that we're going to look at how we are actually going to query this. And first to do that, so how many people have used NoSQL databases before? Can you raise your hand? Cool. How many people are still more comfortable with relational databases? Yeah, I used to raise my hand on that. It's not the case anymore. I grew out of them. But SQL is not my friend anymore, it turns out. But for a long time it was, so no worries. So the query model on NoSQL databases is somewhat different. And let's have a look actually at what that means. And to have a look at that, let's look at a simple database model for a blogging platform, right? We have a few of those at Google, so why not do a use case about it? So I have a table of users and a table of blogs. And it's fairly simple, right? Each user can have access to 0 or more blogs, and each blog can have 0 or more people that contribute to it. That's what we're trying to do. So in a relational model, right, we would actually create a many-to-many table for that relation, and then we connect them together. So this says that user 1 has access to blog 1, so Peter can manage the SF-HTML5 blog, sounds like a good idea. Abe can manage the Firebase and the enterprise blog, and apparently I can only edit the Firebase blog, which feels sort of like I feel left out, but okay, I get it. That one is important to me. So this is pretty simple database modeling, right? We didn't go too much into normal forms yet. Boy Scott would be proud of us, though, so that's pretty good. So, but I need a use case, right? This is just storing data. I need to show data. So how about we try to show a profile page for a user, and we show their name, and we show the blogs that they have access to. Right? Sounds like something very simple. And we've probably written this type of code hundreds of times, right? It's like we start with Abe, right? It's his profile page. Then we find out that he is user 2. So we join the user blogs table, right? An inner join, get all the 2s in there. Then we find all the blog IDs. Then we inner join the blogs table, and we find the titles, and then we display that. It's a lot of words, but we've done this hundreds of times. And it's like, sure, we're comfortable with this, right? We've done this, know how it scales, also know when I'm going to reach some scalability problems, but overall, it's a known evil. And that's not how it works on the NoSQL database. It's very different. So my first NoSQL database experience is App Engine. Whoever used App Engine, and especially its database? Oh, I feel old, I feel old. App Engine was launched 10 years ago. And this was, right, back then I thought it was fun to try all this new technology, which, by the way, I still do. And I was like, sure, I'm going to actually build this blogging platform on App Engine. And I'm not kidding. This was actually something I did. And it's like, OK, so I'm going to store the users, I'm going to store the blogs, right? That's great. And then I'm going to join them together. It's like, where do I store my many-to-many data? And it's like, then you read the documentation, and it says, yeah, you can't do joins. And it's like, wait, these people must be insane, right? How are you ever going to get data from 2 tables if you can't do a join when you need to read it? I think everyone who has done relational databases first and then moves to NoSQL has this experience. And it's like, OK, I honestly didn't know, right? So I was like, this is insane. I'm not going to bother with this platform anymore. And then it's like, this was before I worked at Google, right? And it's like, wait, well, these people at Google, right, they're not really known to be dumb. So I know better now. But so it's like, they must have something in mind, right? They must know something that I don't know. So I started reading the documentation, and what they said is, no. So what you need to do is you need to write every blog that somebody has access to in that user's record in the users table. It's like, okay, sure. And then you write every user that has access to a blog in that blog's record in the blogs table. So this. It's like, oh, okay. That's a lot of data duplication. This is very not normalized anymore for me, right? From a relational background, it's like, oh dear, college teachers would cringe at this. Like, but okay, sure, if that's what they tell me to do. Right? It's like, what do I now have to do to show Abe's profile page? It's like, wait, I only have to read one record here, right? There's only one record, document, thing that I have to actually read. It's like, huh. I can sort of imagine how they lay this out on the disk and how this is a single read operation all of a sudden. Oh, I think I know how it scales so well. Right? Because the database in App Engine was promised to be extremely scalable. And it's like, yeah, I get why. If all you have to do when I read something is read a single cluster from a disk, I get why that would be fast. So writing the data became trickier, but reading the data became a lot more scalable. Who has used Datastore? OK, so Datastore is the database that used to just be part of App Engine. So that's now known as data store, and the reason it was brought out of App Engine as a separate product also is because that it's a really, really good database for scalable read operations, which is good. Trying to figure out what I wanted to explain here. This is our document that we want to store. So imagine that this is a record in the database, right? In the database that we're using. Firestore, by the way, is sort of the spiritual successor to data store, I think. It takes a lot of the good things that you know from data store, and then it adds things like real-time synchronization to it, which is pretty awesome. Right, querying, that's what we were going to look at. So, because I still need to figure out how I can actually query this database. So let's say that I want to get all the documents that are in state WI. Wisconsin? I think Wisconsin. Cool. So all the documents in Wisconsin. So this is the query that you would do on the Firebase real-time database. I'm going to mix query syntax a bit because it's all the same. Right? So we're going to order all documents by their state value. And then we're going to take only the documents that have state equal to Wisconsin, which should be, if it's 10,000 and I have about 50 states, 200, something like that. So sure, right? That's an easy query to do. It's more interesting if I want things like ordered, just ordered. So not filtered, but ordered. Like, I want all these documents ordered by index. It's like, okay, order by child index, or on Firestore, I think it's order by index or something, but same thing. Right? You can easily see how the database actually checks its indexes, right? Finds the one by, in this case, index, and then returns the items in that order. But it gets more interesting if we actually want to get the data by state, or just for Wisconsin, but then ordered by index. Because that on a NoSQL database is not a trivial operation. In fact, on the Firebase real-time database, that's not possible. And now I was on the other side, because remember when I talked about Google and I said these dumbos can't believe that I actually can use App Engine to query and build something. And now I have to actually explain the Firebase side of this, where it's like, yes, these dumbos actually think you can build a real app on a database where you can only order by and filter on one property. Because you can. So remember the use case. We want to get the documents that are in Wisconsin ordered by index. It's a random use case. What if I take the value of the state property and the value of the index property, and I glue them after each other? So I get a list like this. So I create a new property known as a synthetic or synthesized property state index, and I just concatenate the values of the state and the index next to it. So now if I just put all those like synthetic properties in a list, I get state index, California 1047, California 9100, right? And then I get Wisconsin 2041 and Wisconsin 3086, which I think was actually the document we were looking for earlier. Right? I order this synthetic property, and the things are then naturally ordered first by state and then in sequential order of index, which is like, that's an interesting one. Because now if I query this and I order by this state index property and I say start at WI underscore, which is the first Wisconsin, and then end at WI tilde. And now tilde is not a magic operator, tilde is just the last printable ASCII character. So everything in this index is before that. So now I get a range out of this data set that essentially includes everything in Wisconsin in order of index. Sure, I had to pretty much write my own database here, but I think it's pretty cool. And this is what we've been telling people for years to do. This is how you actually can filter documents on multiple values, but still a single property. So you're essentially cheating the system. And that's sort of, I think, the theme of the entire talk is that we're cheating the system. Doing the impossible by coming up with cool data structures. Not the coolest data structure, but still. Firestore actually is a lot better. In Firestore, if I want this, I just tell it that I want this. So in Firestore, I don't have a location, I have a collection. And I say where state equals Wisconsin, and then give me the results ordered by index. Which many people think like, ooh, this is magic. Firestore's query model is so much better. And I definitely agree that the query API is a lot more friendly, but the query model is exactly the same. Because what Firestore does behind the scenes, it actually generates this synthetic index for me. So it generates an index that consists of two values. Now, I've been telling this quite a bit, and then Todd Kerpelman, who knows Todd Kerpelman? He did a video series on Firestore, and he called me out. He said that I did it wrong, because he says that it actually doesn't generate this index. It does something that's known as a zigzag merge join. I mean, Todd calls him ZZMJ because they're friends. They know each other well. So, but apparently it is able to do this from a single index. That's pretty cool, actually. So it's very efficient. And a thing to keep in mind with NoSQL databases is that everything is focused on scalability of read operations. Everything else is secondary. And what's important about querying these databases is that all the results come from a single range. So let's see. Yeah, I still had this one in here. Let's go back to this one. So remember this quite complex sample, right? It's like this is not fun to build. But if you now think of what the database has to do to give you a result, right? It loads this index, right? This property for all the documents. Then it finds the first one with WI underscore. And from that moment on, it knows exactly what it needs to return to me, right? It just starts returning results. It can stream them to me until it finds the end of the range that I requested. So these are known as range queries. And they are the reason why we can scale these so well. And they're also the reasons why the query model is not what you're used to. It's very limited if you're used to relational databases, or for that matter, many NoSQL databases that added capabilities. So real-time database and Cloud Firestore very much will only offer you APIs for things that can scale, not even linearly, not even logarithmically. They literally scale by a constant. So the marketing verbiage for Firestore is that the query performance depends on the number of items you request, not of the number of items you request them from. Very difficult. But what it means is that if you request 10 items and you know how long it takes, good, you now know how your app will perform. Doesn't matter how many documents exist in the collection. Right? When you're testing, it's probably like, in my case, 10,000. Doesn't matter if it's 10 million, it doesn't matter if it's 10 billion. If it takes 1 second to request the 10 documents when I have 1,000, it will take 1 second when there's 1 billion documents. That's the guarantee that Firestore makes. And that's why it doesn't allow you to do certain types of queries, because we can't deliver on that guarantee anymore. Which is all fun and all lots of product mumbo jumbo. It's great when you're talking to the engineers downstairs, but we had a problem to solve. Because how do I query by location? How do I get those documents in the range of 25 kilometers around Sacramento? Remember, that's where we started. So this is a location. I'm not sure if it's a location around Sacramento. We'll check it in a bit, but it's a location. And if we do what I just told you, right, we can combine these two into a single string. You can just glue them together, and I can query for it, right? I can query for both. And it's like, wait, no, I can't query for both, because I can get everything that's between 40 and 42, right? Let's assume the first one is latitude, which it normally should be. Then I can get everything between 40 and 42. But then I can't filter on the second number anymore, right? There's no way I can now still filter on longitude. Like, oh. But that sort of sucks. So let's try something else. What if I take everything on latitude 4167 until 138, right? And then I can filter by longitude, right? Then I can do a range filter by longitude. It's like, yeah, that doesn't help me very much either. It's like, so it turns out that with this construct, you can do many equality operations, but you can only do one range filter. That's actually one of the real limitations of both querying on real-time database. We haven't found a workaround yet. And definitely also on Firestore. You can do one range operation, or a range operations on one value, and not on any others. You can do equality on many of them. So that worked great when we did Wisconsin and index, but doesn't work anymore when we need to filter by location. Because I can get everything in a certain strip around the world, right? But I actually want only a tiny circle here. So that sort of like sucks, right? Because we set ourselves a use case, and it's like, we're failing. So luckily, somebody found some unicorns and found a way to actually make them turn out magic. And the magic is known as geohashes. Who has ever used geohashes? Anyone who said yes to geoquerying must, by definition, raise their hand. Like, cool. So geohashes to me are magic. I started investigating them, and I was like, these things are cool. I mean, I like to geek out. So let's have a look at what a geohash is. Because remember, right, we're still trying to solve the very simple use case of documents around Sacramento. So we need to find a way to query two numbers where actually the database only supports querying one thing. So we need to somehow mesh two numbers together into one thing. And that's what we're going to do. So let's imagine that we split the Earth into two pieces. Let's say one in the top half, the other in the bottom half. Let's, for sake of argument, I like difficult names, call that line that we divide, that we draw in there, the equator or something, right? Just a random line that we've drawn on the Earth. Now we're going to say that everything above the equator is a 0, and everything under it is a 1. It's like, cool. Now with 1 bit, I can identify half of the Earth, right? So I can say that my document is above the equator or below it. Oh, okay, that's nice. Now, let's see. Let's do the same for east and west, so left and right. So that's the meridian. I had to think of what it's called. So that goes through Greenwich, and let's say that everything left of the meridian is a 0, and everything to the right of it is a 1. So now we get this. Now I have a 2-bit value that allows me to identify in what quadrant of the Earth a document is. It's like, huh, that's actually pretty cool. But it especially is pretty cool if I then realize that I can do this for every quadrant again. Right? So now I have 4 bits, and it allows me to determine in which of 16 areas a document is located. It's like, wait, that's 4 bits. That's one nibble. It's like, that's actually pretty fancy, especially since I can find a region. I can keep repeating this. Like, oh. So a geohash has all the properties that you think of from a number, except that it's not a number and it combines two numbers in the same way. Let's have a look at how that works. So this is like sort of the idea behind geohashes. It actually is a lot more complex because they don't use just bits. They use an alphabet of 32. So they have a 32-character alphabet. And this is the first level of the geohashes on the Earth with actual geohash values. So if you look carefully, you can see that at the bottom, it has this little quad that we had earlier, 0, 1, 2, 3. Remember, it's similar. I think I might have inverted them, but ignoring that. Then we move to the right, and it says 4, 5, 6, 7. Then we go to the top left all of a sudden, and it's 8, 9, B, C. So we're missing 0 and A. So geohashes use a dictionary that consists of numbers and lowercase letters, and then they remove the ones that were probably going to be most confusing. And 0 sounds like a very good one to remove. The A, I still don't really know what they thought it would be confusing with. But what is that? There is actually a 0. So wait. Oh, then I know which one isn't there. Then the O isn't there. OK, that would explain. OK. I still don't know why they removed the A, by the way. 6, 7. Yeah, OK, got them. OK, so we're going to keep going for this one. You see that we don't have the O, we don't have the I, because those are definitely going to be confusing. It goes all the way up to Z at the top right. So with one character, we can now identify 32 regions on the Earth. I'm not sure if you can see, definitely you can't see it in the back, but there's these tiny boxes over this. This is actually a tool, we'll see it later, where you just click points on the map and then it shows you the geohash for that. And since I don't just click on the entire N, I click on a tiny box in there, you can see that at the bottom it says N1 is where I clicked. So that's sub-region 1 of the N box. And in the U, the thing that you have there is US, which is somewhat confusing because that's not where the US is. But if we ignore that semantic mapping, then that tiny box is the subdivision S of the region U. This is pretty cool because we can keep doing this, right? We can keep dividing the Earth into smaller and smaller regions that are identified by longer and longer strings. And that's actually fun because now, if each region is a single string and the longer the string, the smaller the region becomes, the more detailed my knowledge is, I can actually query it with Firebase. Huh. This is a list of the size of the region, the cell as it's called, based on the geohash length. I got this from Wikipedia, but apparently our one-character geohash could identify regions of about 5,000 kilometers, which is like, oh, it's a nice first start, right? But when we get to 8 digits, it's 38 meters by 19 meters. So I'm not sure, does anyone know how big this room is? Don't worry, we're going to find it out soon. But once I get to 11 or 12 digits, I'm sorry, it didn't fit on here anymore. It's like, wow, this is some precision work that we're doing here. And keep in mind, that's a string that, okay, I can't really remember it, but 12 characters, sorry, it wasn't digits, 12 characters is actually not that much data. So geohashes are a system that allows us to take a location, right, which consists of two numbers, and turn it into a string that actually then has both those numbers in one value. And that value is magical because from the left of the value, as you move to the right, the meaning, the significance gets lower and lower, which is something that we really like about numbers, and it happens to also be the case for geohashes. It's slightly harder for us to reason off because they're strings and not numbers. That's pretty much the only disadvantage of them. Okay, who knows what this is? Really? This is here. I mean, I didn't know what room we were in, so I took a broad stroke. So this is where we are. So it's a bit hard to read, but it says 9Q8YYZW2. That's here, just so you know. This is where we now live. Okay, let's actually have a look at that. Let's look at some of these properties about geohashes. Okay, different tool that shows geohashes. Wait, I need to actually make sure that I copy that value also. Wow. Let's just jump out of this for a moment. I have no idea where that became hard. We're opening the tool again. So I'm not sure where it starts, probably where the author is, just like we start where we are located tonight. This might look slightly more familiar, especially if you've flown a drone over our building. Not sure if that's legal, by the way, but not sure how we took this picture, so don't know. Okay, this is pretty cool, actually. Now, this is sort of almost half of a floor. And this room is big, but it's not half of a floor yet. So let's see if we can find us, right? So let's add something to it. Let's say that we add a 1. Okay, now we're down on the balcony, but we're actually not on the balcony because there's no balconies on this floor, so we're floating in the air. So let's be careful with that. Let's not do that. So let's do it. A wasn't part of the alphabet. B. Okay. So you can see that all these boxes are still within the box that I had earlier, but they're smaller, right? They're a subdivision of this. So C is probably right next to us, right? And it just goes through that. So I can find tiny boxes, right? This is a small region, and we keep, I don't know how many characters they support 9, but you can keep making smaller boxes if you want, right? We can find where the mixologist is actually keeping his secret ingredients if we want. Okay, so let's zoom out a bit. So, okay, this is where we started. Cool, now we pretty much have all the south part of Embarcadero. That's pretty cool. We're almost at the ferry building. Okay, so this is south of San Francisco, or the southern part of San Francisco, sorry. Apparently doing San Francisco, and half of this is the ocean, is about 4 characters. It's a geohash of 4 characters. Right? And we keep going, and in the end, when we have a single character, this is pretty much what we started with, right? Remember? Who remembers where 0 was? Yeah, 0 was very cold. Apparently, even the penguins get their own geohashes. It's pretty awesome. Okay, so this is how geohashes work. Does that make any sense? Good, because if not, I would have to send you to somebody who actually knows this stuff. Cool, let's go back to the slides. Okay, so we need to store the geohash into a document. Now, if you paid attention earlier, I actually already did that. But let's see how I did that, right? So how do you encode a latitude and longitude into a geohash value? We even have a topic for that. It's probably the shortest topic in here. So how do we take the values from the left and encode them into where we are? So this is apparently the latitude and longitude of where we are now. And it's like, it's this piece of code. This one I can't zoom in, I apologize. But this is all that it takes. So if you would read from the top, the 32-character dictionary is in here. It has the maximum ranges for latitude and longitude in there. And it then goes through a loop, because you ask a certain precision. In this case, apparently, we encode them as 10 characters. Did anyone pay attention and see what the precision on that was? It's probably a few meters, is my guess, something like that. So that's how we encode it. So we loop over the latitude and longitude that you give us. We continue looping until we have the length that you ask for. And then we alternate latitude and longitude. So you see an odd and even check there, right? And we take location 1, longitude, or location 0, latitude. And we just take the next bit of that and we encode it into our geohash. And then when we've reached the length, we return the geohash. This code, by the way, comes from a library called Geofire, which is the library that we use to show those moving buses on the map of San Francisco or major metropolitan areas around the world. And I just copied it from there. Like nothing that I did here. I didn't invent geohashes. I didn't write this code. I'm so lazy. Okay. So this is what we need to store. Let's actually have a look at some of our documents. Sorry, no, let's actually have a look at what this is. Another site. Now this one doesn't show the precision of what we got, but this seems to be where we are, right? So that's actually pretty good. So our geohash translates to this latitude and longitude, which I think is correct. You can also see that there's fewer numbers on the latitude and longitude, so it's not very detailed, but it's hard to see on this side. So let's keep going because it's more fun. I think we just did this. Let's have a look at geoqueries. Now this is where we get to the really tricky stuff. It's actually, I made this as visual as I could because this was fun. The reason I'm actually giving this talk is because we were looking for topics here, and some of my teammates said, well, you've been like talking our ears off about geoqueries and geohashes, so you might as well do a talk about it. It's like, not a bad idea. So, okay, geoqueries. Just in case you forgot, we know we've been here for a while. We want to find the documents within a range of 25 kilometers around Sacramento, what we started with. We now know how to associate a string with each document. These are the geohashes around Sacramento. So you can see that it's 9QB, C, and F because D and E are above it. And then you can see that we have all these 4-character geohashes in the middle of that. Because everything that we need is apparently in GQC, which is actually not hard to remember. So apparently a 3-character geohash is something we can remember. In fact, if you look carefully, where is Sacramento? I think it's somewhere right of the 7. Can you see? It's like it's somewhere around there. Like, okay. So, in fact, we need this box, pretty much, right? This is a good starting point of what we need. Now remember how we query. We need a single range of values from a single property. So that's cool, because if I now start at 9QC4, that's the bottom left, and I go all the way up to 9QCV, then I have everything that I need. It's like, whoa, that's interesting. That's like a type of query that I can do on Firebase. So it's like, I think we're done. Which is not really true. Does anyone see what's wrong with this query, starting at 9QCV and ending at 9QC4, sorry, and ending at 9QCV? Exactly. Good point. So you can see that it actually goes outside of the box. Because remember, we have like just a range, and we pretty much randomly encoded them, not really random, but they were these quads. And I loved the quads until they started doing this to me, because now they're in my way, right? It's like now apparently the quads from 9QCH and stuff goes up there. You can see J, M, and then N all of a sudden. It's like, it's in the way. Like, I don't like this. So it turns out we cannot do a single query for this, which sort of sucks, but let's see what we can do. And in fact, so this was really my first test. My first test was wonderful. Because I picked Sacramento, and it seems that Sacramento is pretty much at the edge of 4 of these quads. It's like, it's wonderful. It's like everything that you can pick wrong about it was in my first use case. I mean, luckily it meant that once I solved that one, everything else seemed to work fine. So what we're going to do is we're going to break what we need, the range of what we need, into 4. We're going to actually query each quadrant separately. So we're going to take everything northwest of Sacramento, everything northeast, and then also to the south. We're going to just do 4 queries instead of 1. Turns out that sort of takes some math, but luckily Geofire has a function for that. So this actually determines the bounding box. If you give it a center and a radius, it will give you the 4 bounding boxes for the quadrants that you need to query. So, and as you can see, it literally just determines some degree math and then converts it to latitude and longitude again. And it gives me 4 ranges, essentially. Yeah, they're literally ranges. I cannot make anything else of it. It's like, let's actually go, to this one. So it's the left of this box to the top right of that box is one range. Then we get this box to the top right of that box, right? So each query has a start and an end. So it has 2 latitude longitudes or 2 geohashes. Here it was still latitude longitude. These are the ones, actually. So let's have a look at them on a map, and I color-coded them. I probably tweeted this one, and people thought that I was playing games, but you can see that I drew them by hand because they're not very straight. But these are actually the 4 queries that we do, and I try to indicate which one goes where. The yellow is a bit hard to read, but it's 9QCD to 9QCH is this quadrant. Okay, interesting, we'll see something there. 9QCH to 9QCN is here, and then we have the other 2 colors also. There's 2 interesting things about this. I will take answers, by the way. Who sees some interesting facts about these queries? No worries, I will give them. One of them is that there's these 2 weird ones here at the top. And I don't really know why they show up, but they consistently do. Many of my queries have a slight outside of the box thing somewhere. I can't really figure out why. So chose to ignore that because it's more fun to worry about interesting things. The other thing is that they overlap. So remember the first one goes to 9QCH, but somehow the red one also starts at 9QCH. Because the quadrants, right, remember, it seems like this is 1, 2, 3, 4 in the order that we had initially. Like, so these overlap. And that means that I could actually merge those 2 queries together. Now, I haven't done that, but GeoFire does that, for example. And then you only have 3 queries that you have to do. And you have fewer duplicates, by the way, because that is the issue with this. I get surprisingly few duplicates, by the way, but not sure why. OK. I think we're almost ready to start querying. Remember, it all started that we wanted like this tiny circle and the documents that fit in it. This is actually sort of like the 25 kilometer around it, so we still have one problem to solve because the boxes fall outside of the circle. It's like, so I'm going to have documents that are in my geoqueries, but that are not in the range that I want to return. Who knows what a Haversine is? Good, I didn't know either. So I thought it was Sir Haversine. I thought he was a famous English mathematician from the Middle Ages. It turns out that a Haversine is a type of sign. It's actually a versine or something. It's a very old mathematical thing. The important thing is that the Haversine formula, which is this one, and you know where it comes from because it comes from GeoFire, actually allows you to determine the distance between 2 locations on a sphere. That's pretty cool because that's literally what we have, right? We have a sphere, it's the Earth, right? We have 2 locations, the thing that we want, the center of the query, and the position of the document, and we just need to know whether it's less than 25 kilometers. So we're going to pass all the things that we get out of the database. We're going to get their actual latitude and longitude, pass it through this formula, and then we know whether they're in range. And that means that we finally can actually get the documents within 25 kilometers of Sacramento. It's like, it took a while. But which is this? I can't say I was impressed when I got it. It's like, okay, whoa, look at this. I got colored markers on the map. But this is literally the documents that we were looking for. Since I know that doesn't get applause in a talk like this, we'll look at it live, don't worry. But I quickly want to explain what we're seeing here. So the green markers are the documents that are within the range that we want. So these are documents that are within 25 kilometers of Sacramento. The red dots are returned by our geoquery, but are not within the range that we want. Did anyone quickly count them, by the way? Because I, of course, did, because why would I write code for something that I can do manually? So it's about 25 green markers and about 50 red markers. So we 3 times over query. I wasn't too impressed with that, but still, it's better than taking the entire strip of the Earth and then only getting the circle. So I think I still won quite a bit there. Let's actually look at this live. It's way more fun. Now I know that you can't read the code in the back. I'm going to zoom the code for a brief moment, and then we'll get back. Whoever used JSBin, or JSFiddle for that matter? Cool. I use them a lot because I like sharing code with everyone. I also like not having to install anything. It's quite amazing. Who uses StackBlitz, by the way? Or Glitch? Or like, cool. I had a hard time getting this in StackBlitz. Otherwise, I would have done that. So I pretty much dumped all the code that I need into a JSBin and then made it work. It took a while. We had people who used Firebase. If you use Firebase on web, then you know that this is an initialization bit. And you also know that I'm not afraid of anyone taking pictures of this screen that contains clearly secret values. So these are not secret. This is actually how you configure your code to find your Firebase project on our servers. Like, there's nothing secret about what I'm showing you now, I think. Well, maybe the fact that I should really support JSBin, but fine. OK, so I initialize Firebase. Now, where it's, and I have the data generator, which is also a JSBin. I generated the data from there. Now, don't worry, I closed off the database after I generated the data, so you can't be adding data to it now. But even if you could, my queries would perform at the same rate as we had before. One of the wonderful things about Firestore. OK, geohash utils. So this is a very long file. We'll look at some interesting bits for a moment, but let's just skip over it for the moment. So geohash utils is the main worker file that I used from GeoFire. And GeoFire is an open source library, so you can just find it. And if you have any questions about it, I'll be sure to find someone who can answer them. It has all kinds of things like converting latitude, longitude into a geohash, finding the split of the box, and simple things like converting latitude and longitude to meters, like bounding box bits, bounding box coordinates, this one we just saw on the slide. OK, I'm looking for the end of geohash utils. There we are, some stuff that we don't need. Then there's the, remember Sir Haversine? This is his formula. So that one came from a different file, apparently. This is the code I wrote. So I know it wasn't a lot. Most of it I copied from somewhere. But still, this is code that I really wrote. Like, if you've never used Firestore, this is how you access it. You get Firestore from the Firebase object, and then you ask for a collection. And remember, my collection was called 10K because I have 10K documents that I spread out over US. Then I have a thing called states. Let's see. We don't see a scroll bar. You have any idea? Like, this is like Alabama, then name Alabama. I have an abbreviation. I have population. I have a capital. Guess what? I have the location of the capital. This line is really, really long because I have 50 states and all this information for them there. Believe it or not, this took me the longest time to get because I couldn't find a good JSON for it. So I created that one. Ignoring that, I have some HTML stuff. Let's ignore that. Not all that important. In the end, sorry, I have two boxes here. I have a pick a state, which is empty at the moment because I didn't run the code yet, and I have distance. If I change either of these, I'm going to draw the, maybe I should just show you. Run with JS. I said if I pick a state, it's going to draw the items around it. Now, this is not 25 kilometers, which is what we promised, so that's the one. But this is what we started with. Now, this is where I will hold for applause. No. OK, whenever you change either of these, we do show map for state by a state and a max distance. Yes, I also have no idea why I left that uppercase. Sloth again. So I do something called get queries for documents around. So I have a state, and I find queries for the document around something. The center is actually the state's capital's location. So that sort of, I hope, makes sense. So that's a function I wrote, which takes the ref, the center, and the stadium. And the ref is the collection, by the way, that we are querying. So it's just some Firestore reference. So then I determine the geohashes to query, which I think I should have somewhere around here. I actually don't know. Sorry, I determined them from geohash queries. That's what I was looking for. So that's a function where I pass the latitude and longitude and the radius in kilometers all of a sudden, or no, in meters, sorry. But ignore that, and then we get back the ranges that we need to query. So remember, we had the 4 colored boxes. Wow, there they are, OK. So this is geohash query, center and radius. We do bounding box bits. We do bounding box coordinates, which you might remember. It's how we split things in 4 pieces. And then we do geohash query, which turns the latitude and longitude into a geohash. OK, let's go back to the bottom where we actually run this code. So I get a number of Firestore queries. Oh, sorry, I should show you the Firestore query. So I loop over all my geohashes that I need to query. And remember, these are ranges from the bottom left to top right, I think. It might also be the other way around. So we do a ref.where geohash greater than location.0. Remember, the geohash contains the latitude and the longitude. So we've just done some magic. I hope all the unicorns are still alive, but we got the magic we wanted out of them, so I'm not complaining. So we do the geohash greater or equal than the first one, and then smaller than the second one. And that gives me a query to Firestore that filters on a single field that has two values. I do all of those, and then I get queries. We loop over the query and we do query.get. So this actually executes the query on the Firestore backend. Now remember, I have 10,000 in there. I'm not sure why I actually named my collections by the number of items in there, because remember, it doesn't matter how many items are in there. I probably had the idea that I was going to create all these collections with more and more to prove that, but clearly not what I ended up doing. So, but this gets me the however many results there are, and that's the performance I'll always get. So we have a Google map, we loop over the query snapshot, which is all of the documents that resulted from this, and then we do a distance calculation, the Haversine formula. And if it's within the distance, then we do some calculation, not all that important, but we add a map to the marker. So I add some stats here. Like, that's pretty much it. This is the entire code that we have here. Like, I admit it wasn't too impressive when I created it either, but what is fun is that you can now play with the values. So, California. Who's not from California? Cool. What state? Whew. Okay. Could also have been somebody not from the States, and sorry, that's all I had in here. What's the capital of Vermont? Thank you. I can't believe this actually is hard to see. We believe that the code is running, right? I mean, that we're not doing anything fake here. So I'm just going to pop it out into its own window, because it just makes it easier to see. Oh, right. I have to rerun it. Sorry, I can't really make this a lot bigger. 10 kilometers, well, this I can definitely make bigger. This is not good. So let's do that. 25 kilometers around Montpellier, you said? Nice, okay. So these are the documents that remember my very, very intelligent algorithm of placing documents on a map, which is called math.random. Place them around the capital of Vermont, around Montpellier. How many people can pronounce that properly? Ha. The advantage of being European. So that's pretty cool. I'm not sure why actually there's nothing here in the top right. I hadn't checked Vermont all that much yet. Any other states that we want to check? I have a few that I want to check for sure. I heard something, but I couldn't. Maryland. Actually, that's a good one. And I like how none of them are on the list of like states that I definitely want to check, because they have some interesting things. Like, okay, Maryland. You can see that I'm not all that picky on where I place them, because half of my documents are in Washington. Like, and I'm pretty sure that Washington is not in Maryland. Reason for that, by the way, is that literally it was random. I didn't do any checks on it. I literally just placed them in a box around the capital of Maryland, and guess what? This is where they ended up. Okay, 25 kilometers, let's do 50. Oh, by the way, here at the bottom, sorry, I should have called that out. We can see the number of documents that were returned from the query and the number of documents that are within range. That ratio is very interesting for me because it's how much we over-query. So we apparently got 79 results, and we wanted only 23. The 23 is green, the 79 is green and red combined. It's all the markers. So it's like, okay, that's 3x over-querying. Keep an eye out for that number. So if we do 50 kilometers, for example, then I get 544 documents, and 81 were within range. So that's definitely not 3 times over-querying anymore. That's about 6, 7 times over-querying. So not good, but still better than, remember, taking the entire 50-kilometer strip and doing that. So still pretty good. What I found as I was going through the states is that this box and its shape is very different in different places. What's the northernmost state? Wow, good. That was not my first guess myself. Yes, Alaska indeed. Cool. What's different about this? It's portrait mode all of a sudden, right? So apparently Alaskans like portrait mode. No, does anyone know why? Because we've seen this difference in shapes before. Yeah, it's further north, right? When we looked at the geohashes initially, remember that the boxes at the poles were a lot higher than the boxes around the equator. That's what we're seeing here. That's actually cool. What's the southernmost state? Yeah. I love speaking for Americans because this is where Europeans would have no idea. It's like, yeah. Indeed, Hawaii. Let's do that one. Like, how many documents do we think we fit in Hawaii, by the way, just out of curiosity? Yeah, it should be about 1/50th of 10,000, of course, so 200. It's like, it turns out that I didn't check for water, so very few documents are actually on Hawaii, it turns out. But, I mean, still, these are on Hawaii. Also see how this box is a different shape again. Now, part of this is the geoquerying algorithm. Part of it is my crappy algorithm of placing these documents, because math.random apparently also just gives me numbers and doesn't take into account that the Earth is curved. So, last thing I want to show, the last interesting use case is, actually no, let's do New York first for a moment. So New York, and let's do 50. By the way, it was a great exercise to actually find all the capitals, state capitals. And I was like, are they sure that's the capital? And it's like, yep. Turns out they were, and they were right. We'll have an interesting one for that in a minute. So 50 kilometers around Albany? Yeah, I saw Muni here, and it's like, okay, so that's pretty cool. Let's go back to California, where we started. Remember, 25 kilometers around Sacramento is where we started. This is 50 kilometers around Sacramento. Yes, thank you. Okay. This was my first test, just so you know. So the map that I showed you initially was not the first map I got. This was my first one. It's like, holy crap, what's going on here? Something is broken, right? Like, something is weird. I saw two weird things here. Who can call them out?
There's the gap, and that's probably because of the lettering system that they're using, the query ranges.
Good one. So definitely the gap, right, is the first one. It's like, why is this box so wide? Right, I noticed that. Now, as we go through the states, which I didn't do, I spent 4 hours figuring this out, by the way. So if you got it right sooner than that, then definitely jobs@google.com is a good idea. But it's like, why do we have a gap in the middle? It's like, I honestly can't figure it out. And it's like, remember my algorithm. I placed the documents, I repeated it intentionally a lot, at a random distance, but in a box from the state capital. Like, wait, what state is to the right of California? That's Nevada. So these are the documents around the Nevada state capital. What's the Nevada state capital? No. Yeah, I really did not know that, by the way. So it's indeed Carson City, that's right here. Now, the documents to the left here look very similar to the documents to the right here. Right, that's the same range of documents that I have here. So it turns out that the geoquery is working fine, it's my data set that's broken. Because I placed them in a box around Carson City and Sacramento, and it turns out that the boxes don't overlap. There's a gap between the boxes. But since I query for the range of 50 kilometers, apparently Carson City is pretty much within 50, but within 50 kilometers of Sacramento. It's like, okay, I did not realize that. So there just is no data in the empty bit in the middle. It's like, that's what happened here. Like, wait, this is weird, right? How broken is my data set? And that's, for me, always even more interesting. I broke something, now let's figure it out. Yes, that worked, thank you. Let's go back to the actual JSBin, because one of the things I liked about JSBin, remember, is that I can change the code. So, let's see. Let's show my HTML. There we go. So this is my dropdown, and the biggest range is 50 kilometers. Where's the fun if you can't do a broader range? So let's make an option that has, how big are the states in kilometers? Let's start with 5,000, and we'll pick a state in the middle. Okay. Let's run this again. Let's actually hide the JavaScript and HTML for a moment. Run the JS. Let's load it again. It was finicky. Don't know why. 5,000 kilometers. What state is in the middle? Kansas. I'll take it. Why are states not showing? What did I break? Did anyone see what I broke?
America doesn't respond to
No, no, no. JSBin might be American, but that's not. Oh, I needed HTML, not the code. Did I forget to close my option or something? Was that it? What was that? I clicked it, right? Didn't I? I did not. Okay, thank you. That was not my best. Okay, 5,000 kilometers. The reason I actually missed that one is because I'm incredibly nervous. We said Kansas.
How many miles is that? 500 kilometers? How many miles?
5,000 kilometers is about 3,400, 3,200 miles, something like that, I think.
Yeah, 300.
Yeah, so it definitely covers the entire United States. I've driven it twice, I know by now. Okay, does anyone want to click for me? Because I'm going to run away when we do this, because we're going to be loading 10,000 documents, so. Okay. Takes a bit longer. Remember, it does take longer to get more documents from the database. It just doesn't depend on how many documents we have. Cool, we loaded 10,000. They're all green, which sort of makes sense. Let's zoom out a bit. Okay, wait, we're still missing something there. Yes, and you know what? Hawaii is not within 5,000 kilometers of the capital of Kansas. Like, something we learned today. So this is my data set, and if we now zoom in, you can easily see that we actually do have a gap between these two. Lesson to be learned here is that you should always first test with the broadest part of your data set and only then zoom in. No, actually, lesson is that it's fun to explore and hack these things. So this is the gap that we were seeing earlier. It started with such a simple question, remember? All we wanted to see was things within 25 kilometers of Sacramento. It sounded so simple. All these apps make it seem so simple, and that's the reason because some people do this magic work behind the scenes. I think we just covered all of the interesting edge cases. I'm not completely sure, but I think I had most of them.